Hi guys, I'm going through the latent heat diffusion question that came up in the 2019 higher level paper. So that's the question in front of you there. Now I have a couple of calculations done on it, but really what I want to go through and I want to show you in this video is the calculation, how you set up the calculations for these questions. Now this applies to the latent heat diffusion. It's an almost identical process when you are dealing with the latent heat of vaporization questions as well. So let's have a look at what we are starting with here in this. Okay, so just to remind you, I suppose, of what's going on in the experiment, you're taking a calorimeter, which you can see here in the red. You're putting water into it. You take the mass of the calorimeter and the water, and then you are crushing ice and putting it in. Now, the initial temperature of the water is taken before the ice goes in. You add enough ice to usually drop the temperature by about 10 degrees, and then at the end stir it, make sure it's all melted, and then take the mass of the calorimeter, the water, and the ice at the very end. This will allow you then to find out the mass of the ice. What's happening there is the ice is melting. Now, it needs energy to do that, and it is getting its energy from the water. So the water is losing energy. And because it's losing energy, it's getting cooler. The temperature is dropping. The calorimeter, it's made of copper, and that is obviously cooling as well. So if the water temperature drops, then the calorimeter temperature drops. Now, when you're doing these questions, this should be your starting point. Look at what is gaining heat and what is losing heat. So in this experiment here, what's gaining heat, what's actually taking the heat in, is the melting ice. So that needs heat to melt, okay? When that ice is melted, you have ice water, I suppose, at 0 degrees. That is going to warm up to the final temperature of the calorimeter in the water. So that needs energy as well. Those are your two things. What provides that energy or gives it the energy then is what is losing heat. And that's the actual water in the calorimeter and the calorimeter itself. Now, the reason that you start with setting it up like this is that heat energy lost or gained is given by just one of two equations. It's either going to be, if the change of state happens, the equation ml. If there's no change of state, then it's mc delta theta. So you're dealing with blocks of energy that are calculated using mc delta theta or ml. Simple as that. Now, once you do that, then it makes the whole calculation a lot more manageable once you break it down into that. Because you know what's on the left-hand side over here must equal what's on the right-hand side over here. So the energy, because the ice is melting, it's changing state, it's given by the equation ml. You know what the mass of, I should have an I beside it there, that is the mass of the ice, okay? L is what you're trying to find in this, so you're not going to have a value for that. The melted ice, that obviously is the same mass of ice. It is water, so the specific heat capacity of water is what goes in here, and the change in temperature. Now, this can catch people sometimes because you're not given an initial temperature. Well, when you're melting ice, the initial temperature is 0 degrees. So the final temperature is the actual final temperature of the total calorimeter in water. The water cooling then, again, how much water, mass of the water that's in the calorimeter, the specific heat capacity of the water, and the change in temperature of the water. This is taken from your initial and your final temperature. The calorimeter, very same thing, with the mass of the calorimeter and the specific heat capacity of the calorimeter put in there, and the change in temperature will always be the same as the change in temperature of the water. Calorimeter and the water are always the identical temperatures. So think of holding a cup of hot tea. The cup and the tea are usually at the same temperature, unless it's an insulated cup. But yeah. So where do we get those figures from? Well, you come back to your question. At the bottom of the question, will any specific heat capacities that are needed are going to be given there. You do not have to remember those. And when you come up to the information that they give you in the question, the mass of the calorimeter is here. That's fine. Now, this is generally the way they give you the mass of the water. They give you the calorimeter and the water together. So you just subtract the calorimeter from this and you're going to get your mass of water over here. The initial temperature of the water, the final temperature of the water. Remember, this is also the final temperature of the ice water as well. And again, this is the trick to find the mass of the ice. This is your calorimeter, your water, and your melted ice water all together. So you subtract this value up here away from your 122.9, and that gives you the mass of the ice. Now I have all of these in grams. When you put them into the formula, I would strongly suggest that you use kilograms. You can get away with using grams in this as long as you have grams on both sides. But as soon as they ask you anything about energy, how much energy is needed to melt the ice, or any questions like that, that formula only works when there is kilograms in there. So just make your life easier, change everything into kilograms. There are all the values in here, and then you're going to solve that equation. You can work out this, you can work out this, add those two together, and then subtract this from it, and you can work out a value of L from there. Now, to do that straight off is a difficult thing to do, okay? And this is what throws people off these calculations, is they just look at and see a whole load of numbers and remember, oh God, that was a really long, messy calculation, and sure, I'd never be able to do that and put that together. Break it down. Start with what's losing heat, what's gaining heat. This will get you marks in the exam, just writing that sometimes. And it's easy then to go from there to, okay, well, what's gaining heat? That's increasing in temperature or melting, or usually it's 2 on this side and 2 on that side. For your latent heat of fusion, latent heat of vaporization, it's 2 and 2. When you're talking about the specific heat capacity, it is 2 and 1. Okay, but again, specific heat capacity can be approached in the very same way. What's losing heat? What's gaining heat? Okay, that's it. Oh, that's a picture of a calorimeter, just in case you don't know what a calorimeter is, but it's very important because they're always mentioned down there. Okay, thanks guys.